Hello and welcome to this contributed talk to CCA 2020. I'm Martin and this is a joint work with Jiman, Hwang and Svetlana, and actually the main part will be presented by Jiman. I will only talk about the first two slides. So this occasion of this contribution is that iRRAM was presented to the public 20 years ago. Norbert had been developing it before that, but the public version was released in 2000. And so this is an opportunity and time to look back and, more importantly, arguably, to look into the future. The future of exact real computation, a paradigm that arguably has been established by iRRAM. So what is the essence of exact real computation? It's to have continuous abstract data types and thus complementing all the discrete abstract data types that have been prevalent in classical computer science as well as in computer algebra. For instance, computers operate on bytes, but the abstract data type allows to operate on integers without having to worry or take care of wraparound effects. And building on that integer abstract data type, a computer algebra system may implement, for instance, an integer polynomial abstract data type, and building on that, taking quotient with respect to some primitive polynomial is a common way to implement algebraic field extensions. So it's an entire hierarchy of abstract data types in classical computer science, but they're all discrete or symbolic or algebraic, if you like. But the novelty of iRRAM is to provide real continuous or analytic or transcendental abstract data types, and the most important one are, of course, the real numbers. Recent real numbers have been introduced to mathematics as opposed to, say, rational numbers or algebraic numbers is their properties, right? So specifically, for instance, the intermediate value theorem. And this is what iRRAM actually achieves, real numbers exactly without rounding errors. So underlying the implementation is, of course, still floating point numbers, which do incur rounding errors. But this new layer of abstraction hides all these details and allows the user, allows us to write programs that operate on and manipulate real numbers in just the very same way that one actually intuitively conceives that in both numerics and in pure mathematics proofs in calculus 1 to 4. And building on this real number abstract data type, iRRAM also supports vectors and matrices and polynomials, and all to agree, fully agree without rounding errors, to agree with the similar structures in the sense of model theory from calculus. And we recently have added to this variety of continuous abstract data types, abstract data type of subspace, linear subspace, that is the Grassmannian. This is the work of Sokbin Lee, who is now a student at Georgia Tech. iRRAM supports sequences and power series, and based on that, Holger Thies has implemented analytic functions, in particular analytic continuation, which is very messy to do with classical numerics because of all these rounding errors and precision considerations. But in iRRAM, you can implement, and he implemented this just the very way that one conceives and learns in function theory. And iRRAM supports continuous functions, and we're planning or suggesting to extend that to smooth functions, let's say C3, C4 function, as well as to integrable, not necessarily continuous functions. These are like L2 functions. These are the kind of functions used in partial differential equations. Further suggested extension are compact Euclidean domains or bounded operators. So generally speaking, our first suggestion for the future of exact real computation is to add more of these continuous abstract data types to the library that iRRAM already and natively supports. The first suggestion. And the second suggestion is to modularize computation. And let me to remind you, bytes underlie discrete computation, or maybe your computer has words or double words or quadruple words, but in practice users don't really need to know about this anymore. This is different from like 30 years ago, because nowadays most programming languages support mathematical integers without all the hassles of wraparound effects. For instance, in Java this is called big int, in Python it's called big num. And of course, in order to realize this, between both ends there must be some translation, a library. For instance, if your programming language does not natively support mathematical integers, then the GNU multi-precision library still allows you to do that both efficiently and conveniently. And in terms of efficiency, for instance, a naive way to implement unbounded integers on top of bytes is to use long multiplication from high school, and synthetically fast is Karatsuba's algorithm, Thom's algorithm, Thom-Cook family of algorithms, fast Fourier transform, Schleifen-Schönhage, all these algorithms, but the user doesn't need to worry or care about this, because that's all part of the library. It's all part of the continuous abstract data type. Now let's look at the same situation in the real case, where the user program executes command in this exact real computation paradigm, operating on real numbers, supposed to be exact without rounding errors, but in practice, in hardware of course, there's finite precision, maybe arbitrary precision by combining or varying the precision, but it's always finite precision. So again, one needs a translation, some library in both between, for instance, MPFR provides such arbitrary but finite precision computation, and the library needs to bridge from that to exact to infinite precision computation. And this is what I'd like to call an exact real computation engine. It's something which executes or simulates the user code with finite precision chosen carefully, sufficient such as for the user program to behave as if it were executed with infinite precision. And choosing that precision is a delicate issue. I will not go into detail here, but the point is that various libraries provide such an engine. iRRAM, our birthday child kind of, does that by keeping track of the precision, and when it turns out that the initial precision was insufficient, then exception is raised, and iRRAM silently re-executes the user program transparently in such a way that the user program does not notice it has been re-executed. In this way, for the user program, it appears as if the precision was always miraculously sufficient, or put differently, as if it were infinite. And there are different other ways to achieve the same goal. For instance, one can keep track and store symbolic representations of the expressions computed by the program. This allows to reevaluate the expression in higher precision if the initial precision is insufficient, without having to re-execute the program. But of course, the disadvantage is that this takes much more memory. The advantage is that it takes less running time. So there's a trade-off here involved. Of course, I also must mention the Core2 library developed by GEAP. Now, iRRAM is closely tied to the MPFR library as a library providing this arbitrary precision, finite but arbitrary precision computation, which there's already a modification. Initially, iRRAM uses the hardware double precision, and when the first exception strikes, when this turns out to be insufficient, then iRRAM starts again with software support by MPFR library, and this incurs a huge penalty in efficiency, and Jiman will tell you in a minute how he has been able to avoid that huge penalty using double-double, two hardware doubles, and using quadruple double. But there are other ways, conceivable ways to accelerate this arbitrary precision computation, for instance, with hardware, dedicated hardware like field programmable gate array or application-specific integrated circuits. This is something that Fritz Meyer-Lindenberg from Hamburg Technical University is doing. And so the suggestion we'd like to make here is to remove the ties between iRRAM and MPFR and to make it modular so that any arbitrary precision library can be used, including MPFR extended with double-double or with hardware, and also to modularize the engine so that the user program can be executed on various possible engine, iRRAM or Core 2 or RealLab. So that's the end of the first part. Thanks for your attention, and now I pass on to Jiman.
Hello, I'm Jiman. As Martin already mentioned, when iRRAM moves from double precision to arbitrary precision, there is an inefficiency. I will explain this in detail and how to cope with this. Okay, let's first take a look at the performance of a multiplication. Multiplication is important as it is used by other operations like exponent and divisions and so on. So we want to improve the multiplication mainly. So let's take a look at this graph. When iRRAM starts multiplication and if we increase the multiplication precision, then iRRAM starts with double precision, which has a 50 bits, around 50 bits limitation. If we need more precision, then iRRAM moves on MPFR. But the problem is this performance gap between these two these two different data structure. Our goal is to smoothing this transition by implementing multi-double. It looks like this. So what is exactly multi-double? Okay, multi-double is nothing but multiple doubles. So before explaining that, we would like to explain double-double instead. Okay, double-double is nothing but using two doubles as an unevaluated sum. For example, if we are given this number, then we can take this number into two parts. Okay, assume that we have a 4-bit precision for each double data structure. For explanation, then we can take these two rectangular edge components so that we can represent the number A into this representation. So we are storing one number into two components or two doubles as an unevaluated sum. Okay, and the all algorithms based on this data structure is also component-wise. For example, if you want to multiply two double-double, then we take these numbers or these components and multiply them, also 3, multiply them, and then we add up by column, and then we have to, in this case, abandon the last or the smallest component, as double-double only store 2 components at maximum. Okay, one advantage of this data structure is that it is supported by hardware, so that it runs fast at low precision. But the problem is due to this disaligned data structure, it is very hard to come up with a decent algorithm. So it runs very slow at the high precision. So this is why we want to implement this double-double or multiple double at the low precision. Okay. In fact, we haven't no idea about this kind of data structure can overcome the MPFR's performance. So we have tested two experiments. In one test, we have done matrix and polynomial test, polynomial multiplication test with implementation of each element, double-double and MPFR. Okay. A double-double precision is 103 bits, and we have set MPFR like around the 103 with not just one with various size, but still similar to 103. And in the second test, we have done exactly the same thing, but with different implementation. This time, we have used a quad double, that's 209 bits, and similarly, we have used the MPFR with similar size. Okay, some may wonder why we have used the matrix multiplication and polynomial multiplication. Well, we want iRRAM 3 to be used in practice, so that's why we have used matrix and polynomial multiplication, which are frequently used in science and engineering. Also, we have in these tests we have used long multiplication only, not without any advanced multiplication algorithms, and also use the QD library, that's implementation of double-double and quad-double developed by David Bailey. Okay. In the first test, we have calculated the time ratio, the calculation time taken by MPFR over the one by the double-double. What does it mean is that if this time ratio is greater than 1, then double-double outperforms MPFR. Okay. In the matrix multiplication, we have increased the matrix size represented on the x-axis, and we have used MPFRs of variant size but similar to double-doubles. We can interpret this this graph by putting this number 5 and say that all the time ratios are plot over the number 5. That means double-double runs faster than MPFR at least 5 times. Okay, and then similarly in the polynomial multiplication, we have increased this time order of polynomial. And then we can put number 5 here by saying that time ratios are above the 4. So in the first test, you can conclude that double-double runs at least 5 times faster than MPFR does. Okay, this is the second test. We also used the time ratio. This time used the quad double time. And also, what does it mean is also the same. If this time ratio is greater than 1, then quad double runs faster than MPFR. But test result was not that promising. The time ratios are around the number 1. That means that MPFR and quad double runs very similarly. I mean, the time taken by two different data structures are just pretty same. And in polynomial multiplication, in this time, all the data are below the number 1. That means MPFR is faster than quad double. So in the second test, we can conclude that QD does not beneficial to implement. Okay, we have also tried on slightly different things. Extended double-double. Okay, X87 chipset, that's in your PC, or almost every PC has this X87 chipset that provide extended double. That looks like on the left figure. It is a little, as the name said, it is a little extended version of double, providing 11 more precision. So we wonder if this extended double give us some more gain over the double-double. So we have tried extended double-double and tried exactly the same test that whose result is expressed in this slide. Extended double-double provides more precision at the cost of more time. If this more time is very big, then it is better not to use this extended double. That's why we define the cost and gain. We define cost as the time ratio, the calculation time ratio, and we define the gain as the precision ratio. By comparing these two, we will decide whether it is worthwhile to use extended double. Okay, we have done exactly the same test, and we have plot the time ratio, that's the cost. And also we can draw the gain as a line, horizontal line, that's approximately 1.2. As you can see, the cost is fairly above the gains. So our conclusion is that this extended double is not worthwhile to try as for the efficiency region. Okay, let's conclude this talk. Going back to the first slide, the iRRAM used the double data structure for initial precision, then moves on arbitrary precision. But now you can put this double precision that provides almost double precision, and you can also provide extended double, but for efficiency region, we will not implement this extended version. We can also take a look at the quad double. It provides even more precision, but it is not worthwhile because due to its performance, quad double also it is not worthwhile to implement. So our conclusion is it is worthwhile to try double for iRRAM 3. And future work is, of course, implementing this double into the iRRAM 3. Thanks for listening to talk.